In less than 5 years, an astronaut will be stepping out on the moon to conduct man's first real exploration of our oldest satellite. It will have been a long voyage, carrying him far from his native land, planet Earth, into a strange and airless world. To survive, he must carry with him a bit of his familiar environment. How bioengineers are designing a spacesuit that will support astronauts on a round-trip lunar mission is our story today on Science Reporter.
I'm John Fitch, MIT science reporter, speaking to you from the moon, or at least a reasonable facsimile thereof. Actually, the simulated lunar landscape and this mock-up of the Lunar Excursion Module are at the Manned Spacecraft Center in Houston, Texas, where engineers for the National Aeronautics and Space Administration are testing and evaluating the performance of the Apollo spacesuit. Actually, encapsulating a man into a suit that protects him from his environment at the same time gives him adequate life support is no very novel idea. Deep sea divers have depended on just such a solution for their descents into hostile ocean depths for decades. But as it applied to going up instead of going down, bioengineering got a much later start. It wasn't until World War II, when airplanes began nosing up to an airless 20,000 feet, that man found he was stretching beyond his natural reach. Breathing oxygen systems had to be devised. And not so many years later, men flying high-speed military planes at ever higher altitudes required anti-force and decompression protective systems. But today, as we move into the space age, these few problems seem relatively tame when they're measured against the support systems that man will require for lunar explorations. And to find out about these systems that will be used to protect men on the moon, we talked to Mr. Matthew Radnofsky, Assistant Chief of the Systems Development Branch here at the Manned Spacecraft Center.
John, before I show you the Apollo suits, I think you ought to see a couple of our earlier models. Here we have the Al Shepard's suit. This is the Mercury suit. Some of the interesting things about this suit are, note that there aren't any movable joints in this. No hard joints, no sealed rings or anything else. All mobility is achieved by very clever tailoring. You can see artificial brakes that have been sewn into the suit, realizing, of course, that this entire suit is simply but a bladder and that the restraining garment on the outside is what allows us to have mobility. Note in the elbows that we have no special joints, simply through the use of this unidirectional restraint, we're able to get a certain amount of mobility in the elbow.
I mean, if you didn't have that, you'd just sort of be out like a balloon?
Exactly. He would inflate and be almost rigid. He just about couldn't move at all. This green bottle is interesting. This is the way we originally sealed our helmets, the visors. See, this visor moves up and down, and by inflating a seal that's around the periphery of it, we achieve quite an excellent sealing of the entire suit.
Was this a really significant step forward in suits, or was it?
Not really, because this suit is really based on a developmental item that came from the Navy. This suit, as it stands, is very similar to the Mark IV Navy suit, which is used in conventional high-altitude aircraft with some minor modifications. In the hand, we've added a different kind of a palm restraint in here. But generally speaking, this suit doesn't differ significantly from the Department of Defense model. At the moment, he's simply being ventilated by a ventilator here, which keeps him cool until he would be attached up to the spacecraft itself.
What about the next step?
Well, the next step after the Mercury suit is the Gemini, and here we have.
Oh yes, this looks familiar.
This is a suit very similar to this. In fact, identical to this was worn by White in his extravehicular excursions. This suit is covered with a material called Nomex, a very high-temperature nylon, which will withstand very high temperatures, about 700 degrees.
Is that because the sun's shining on him out in space?
Yes, although under these circumstances, this is primarily used in case the spacecraft itself got hot on the outside and he touched it, he wouldn't be burnt. Also, it would protect the material underneath. Remember, the temperature outside can be up to about 250 degrees.
Well, now, this actually had to support life for him out there in space with nothing but an umbilical cord.
That's right. Under White's flight, or in White's flight, he received his oxygen through this port, through a long umbilical, and it was simply ventilated through him. Part of the flow rate of the oxygen came down over his visor, right here. And also, it might be interesting to note that he used very low flow rates because he didn't do that much work. He worked hard, but not much harder than he would normally, either inside the spacecraft or, for that matter, on Earth. The suit itself was equipped with glove lights. I don't know if this, yes, we have them shown here, which allow the man inside the spacecraft, when he was inside the spacecraft, to scan his instruments without destroying dock adaptation when he was on the dock side of the Earth.
Well, now, what kind of a suit will they wear on the way to the moon?
On the way to the moon, inside the cabin, they probably won't need a suit at all. Let me come over here and show you what they will be wearing. Here's our constant wear garments.
Oh, really? This looks like a set of long underwear.
Well, that's just what it is. It's a modified set of long underwear used as a carrier for the electronic equipment for amplifying the signals that come out of the biosensors. Here's one of them is hanging out now. This is stuck right against the skin on the inside.
Let's see. Well, you mean this is all they have on inside the...
That's all they'll have on inside the command module. There's no reason for a suit. Remember, the main reason for a suit is to protect the man against low pressures, very low pressures, and at the same time, in the event of returning to the Earth, they would have to have environmental protection against the Earth's environment, hostile environment, in an emergency. But normally, under normal conditions, we don't expect them to wear a suit. A true shirt-sleeve environment is what we expect to achieve.
Well, then, once they do get to the moon, though, can they wear something like the...
That's something else again. There's a whole series of problems associated with the very hostile environment of the moon. For instance, we have to protect the man against the thermal loads that he will encounter in working very hard on the moon's surface. We have to protect him against the micrometeoroids, which are a constant source of potential danger, and also the secondary ejecta. These are the splashes of rocks that come up when a single meteoroid would hit the ground, let's say, close to the astronaut. We have to protect the man against the infrared and the ultraviolet radiations, which are not at all reduced by the lack of a atmosphere around the moon. We have to protect the man against the very hot and very cold temperatures associated with the surface of the moon. There are a whole series of them. We have to provide the man with a self-contained life support system. This life support system would include a whole series of items which we can discuss later, and which I can demonstrate to you quite easily.
Well, now, how are you going to solve all these problems?
Well, it's interesting. Here we have an indication of our...
Hand with us.
Thank you. Here I have a mannequin dressed in a liquid cooling garment. If you'll note, the inside of this garment is covered with small tubules. These little tubules are filled with water. They are actually filled prior to flight. And by conduction, by causing a flow of water through the main branch and then returning it from this secondary branch, we have the ability to pick up heat directly from the skin, which keeps the man's temperature, skin temperature down, and therefore stops him from perspiring.
Well, now, why can't you just use the regular air conditioning with
Normally you do. Normally you do, simply blowing cold, dry air across the skin, and this is supposed to pick up all the perspiration associated with his work. But on the moon's surface, we expect the man to work very hard, extremely hard, almost twice the rate that he works on the surface of the Earth. As a result, his work rate is so high and his production of perspiration so great that we can't possibly pick it all up by the rate and the amount of gas available in the portable life support system.
Well, now, does he wear this thing over that or under?
No, this is one immediately over a very light set of skivvies, or a light set of underwear, and directly under the pressure garment assembly, which we have over here.
Oh, could we see that? Oh,
Sure.
I'll get rid of this for you.
Thank you.
Oh, this does look quite a bit different from that Gemini suit that we saw.
It is. This is one of our earlier models of the Apollo suit. Note the joints particularly. This is a demonstration of a constant volume joint concept, which was submitted to us by one of the contractors who ultimately won the contract for the moon suit.
What do you mean by a constant volume joint?
Well, under this design, or in this design, the man can move, and when he moves, he doesn't disturb the column of air so that the internal pressure remains constant.
Oh, he isn't trying to squeeze air when he tries to move.
Exactly. If indeed he'd squeezed air, the force and work associated with doing that would almost prevent him from making any sort of motion. There's a great deal of work anyway, and we want to keep this to a minimum to make normal motion. He's not pressurized at this time, again, being ventilated simply to keep cool.
Could we see the actual Apollo suit?
Yes, let's take a look at the suit now.
It seems to me he's walking a little more stiffly than the other.
Well, this
fellow.
man is pressurized now. He has 3.7 psi. That is, there's almost a little over 3.5-pound differential pressure in his suit. It's slightly inflated, a little more than the previous suit.
Is it all right to...
Surely. But you can see that there is a considerable pressure associated with this mode of operation. The gases are ventilated. The incoming gases come in here, go up to his helmet, and then pass over the front to stop it from fogging. And a portion of the gases. The rest of the gases go down to the extremities, to his fingers and to his toes, and then come back, are collected, and come back through here.
When the astronauts leave the LEM for their exploration of the lunar surface, they'll strap on one of the most important parts of the extravehicular mobility unit, the Portable Life Support System, or PLSS. To learn about this unusual backpack, we visited the Hamilton Standard Division of United Aircraft in Windsor Locks, Connecticut, where the PLSS is manufactured. We talked with Mr. Ronald Lang, project manager for systems engineering.
Here in our space lab, I'd like to show you a full-scale mock-up of our portable life support system, or backpack. This, when used in conjunction with a pressure garment or spacesuit, gives a man all the required essentials for life support. As a matter of fact, it has everything that a spacecraft would have, with the exception of a propulsion system.
You don't have any rockets.
No, we use our legs for the propulsion. When a man wants to put this on in the vehicle, he disconnects the oxygen supply that goes to the suit, that's going and coming from the suit. He disconnects the water that goes to the liquid-cooled garment and back, and this is an emergency oxygen system that goes into the helmet, and then an electrical umbilical. And then to put on this backpack, he faces it in this fashion, turns around with the pressure suit on, and then connects these all to the proper connectors on the suit.
And this just has a harness that fits over his
It
shoulder.
just puts on a harness. It weighs about 65 Earth pounds.
That's pretty
but,
heavy.
on the moon, it's only about 11, 12 pounds.
All right, because of the reduced gravity.
Right. Now, as a life support system, it contains all the basic ingredients for life support. Chief among these would be the supply and regulation of high-pressure oxygen to the suit. This oxygen bottle sitting right here contains a little bit over 1 pound of oxygen. It's at 850 psi, and it's regulated down to suit pressure of about 1/4 of what the pressure is in this room.
Would that be a little uncomfortable?
No, it wouldn't be, because it's pure oxygen. And as far as a man is concerned, his lungs see the same amount of oxygen as they do on Earth.
See.
Now, as the oxygen goes to the pressure suit and picks up carbon dioxide, it brings it back through these umbilicals to the backpack, and a backpack must remove that carbon dioxide. Otherwise, it'd be lethal to the man.
Really?
What we have to do then is use a chemical absorption bed. We have a contaminant removal cartridge that removes odors and carbon dioxide. Best to show you then a cartridge, which is a replaceable. We use one of these with each mission. It contains lithium hydroxide and activated charcoal, and it's completely consumed at the end of a mission.
It's sort of like an oil filter.
Yes, it is. And incidentally, it gives off heat during this process. It adds heat to the system. And I should add that for that to be effective, the fact that it's sitting here by itself doesn't do us any good. We have to come up with a technique for getting the CO2-laden oxygen from the helmet to the backpack.
Right.
And for this reason, we use a fan. And the fan is this gadget right over here.
Oh, I see.
That is a fan, and the fan is powered by an electric motor. We also use a pump to push the liquid cooling, the water, to the liquid cooling garment and back. The pump sits right at this point, and it is also powered by an electric motor.
Well, that's right. To send the water over there and bring it back. And how do you cool the water once it's inside the backpack?
The water has picked up about 8 degrees when it goes through the liquid garment, and the oxygen is coming out at body temperature, and it has a lot of moisture in it. And this is all cooled in this box right here, which is a sublimator. Now, a sublimator is best described by referring back to the big snowbanks in Maine that seem to disappear even though the temperature never goes above 32 degrees. What happens here is that the snow goes directly from the ice phase to the gas phase, and it never melts in between. So the principle of operation here is exactly the same. What we do then is and let me show you, by the way, this is a sublimator, a complete and actual sublimator. The oxygen from the suit comes in through here and leaves here. The water comes in from here and leaves here. The water that we are turning into ice to sublime is coming in from here to here from a reservoir. And what it does is it becomes an ice layer in the layers in here, becomes ice, and to enable it to go from ice to gas, it must pull heat away from its surroundings. It cools this whole assembly down to almost 32 degrees. In fact, the ice is at 32 degrees. And in so doing, the oxygen and the water that go through here are cooled down to the levels that we have to have.
Yeah, it's very interesting.
Well, we have other things that are in this backpack that are not life support elements per se. Chief among these are communication. We have a communication subsystem which sits right on top of the sublimator and is cooled by it. This is the antenna, and this is the connection here.
So that he can talk back to the LEM?
Exactly. He could talk back to the LEM, or he could talk to the Earth via the LEM.
A little radio station.
That is a complete transmitter and receiver. I'd like to show you a component there. This is the communication system.
It is really small, isn't it?
It's very small and very compact, and it has, in addition to voice, it has 7 channels of information that are continuously telemetered. If the man so desires, he can shut off the telemetry. It monitors the performance, and it gives us an EKG, an electrocardiogram.
Now, just thinking that all these things seem to run on electricity, how do you power all of this for 4 hours?
We power the electric motors and the communication system with a battery, a silver zinc battery, which is also a one-shot deal. We have as many batteries. The battery goes right in here at this point. And there are as many batteries as we're going to run missions. It's 5 pounds, and it's designed with the launch vibrations in the vehicle from Cape Kennedy in mind. It's a very rugged, reliable battery.
And that's enough to run this for 4 hours?
It's enough to run this for 4 hours. Yes, it is. The other thing that I'd like to mention is failure detection. For us to be able to run a successful mission, we must feel confident that we could bring the man back in the event of a failure. And the astronaut will have on here various systems to tell him that he's got problems, if he in fact does. 2 of these will be a low-pressure warning device, which will trigger an audible warning buzzer if the suit pressure goes below 3.2 psi.
How would that happen?
If we had a leak in the system, or if for some reason we stopped supplying oxygen, the pressure would begin to decay. The other thing that we would like to tell him about is if we're using up too much oxygen. We have a flow warning buzzer that tells him, you're using your oxygen too fast. Do something.
Well, if he does get into one of these serious problems, how is he going to get back when he's wandering around in the moon?
He has an emergency mode of operation. He immediately cuts in his emergency oxygen system, which is built onto here for expressly that purpose. The emergency oxygen system is a toroidal, 7,500 pound per square inch supply that contains only 0.2 pounds of oxygen. And when used in conjunction with the main supply, can give us emergency ventilation and purging of the helmet area, even though the fan fails. Now that thing will go in this area up against the backpack. Another emergency system is the communication. We have a redundant communication system.
to see the rest of the spacesuit to be worn on the moon, we talked again with Mr. Matthew Radnofsky at the Manned Spacecraft Center in Houston. This white garment, what is that for? Does he wear that?
This is his thermal meteoroid garment. It's made up into layers. These are the layers of material. The first layer is a Nomex cloth. This whole garment provides protection against radiant energy impinging on the suit from the sun and also reflected from the moon, and also protects them against meteoroids. This is a most interesting insulation. This insulation only works in a vacuum. It's very similar to the material that we have in a thermos bottle on Earth. It's as though the man were completely enclosed in a thermos jug.
There's so many layers.
It consists of some 7 or 8 layers of aluminized mylar with a Dacron scrim, and then covered with the abrasive-resistant Nomex material that we've talked about before, and also has this felt layer, this nylon felt, which provides the bumper protection against the meteoroids that we also discussed. For instance, on the lunar surface, we have meteoroids, micrometeoroids, which are constantly hitting the moon. Even if they don't hit the man or only hit close to the man, they travel at immense speeds, something like 30,000 feet per second or higher. And as they hit the moon, they send off showers of rocks, which also have high energies associated with them. And they themselves, traveling at very high speeds, could injure the man were it not for the protection afforded by this soft layer.
Now, how big are these micrometeoroids?
They're not large. They run from 5 micron in diameter upwards.
So like a little speck of dust, isn't it?
Yeah, you can't see them actually. And as I said before, they run something like 10 times the speed of a bullet.
So they have a lot of energy, even though they are
a great
small.
deal of energy. They are so fast that one could possibly never know it again either.
I see. These are very unusual shoes that he has on top of his regular shoes.
Note that this portion of the suit provides protection against radiant energy. The boots provide protection against conductive heat loss or gain through the soles of the shoes.
You mean the surface of the moon could actually be hot to touch?
The surface of the moon will probably range between plus 250 degrees and minus 250 degrees. And the heat loss through the boot soles could be tremendous. Then, of course, we have our visors, and these give protection against both ultraviolet and infrared rays, resulting from the lack of an atmosphere around the moon. Normally on Earth we have an atmosphere which filters out to a great degree the harmful radiations from the sun when they are intense. On the moon we have no such cover, and we have to provide it. If it weren't there, then he would become blind, he'd have retinal burns and so forth. He must have this kind of protection.
These fold down over his regular
These come down
faceplate?
over his visor. The one is for the infrared and the other one for the ultraviolet. They also provide visual protection in the visual range, the visible range.
So like big sunglasses?
Like big sunglasses, exactly.
Well, with all of this material on, I wonder how he can do anything but just sort of stump around a little bit.
He actually can do quite a bit. Do you want to show him some of the exercises? Now, he's pressurized here, 3.5, 3.7 pounds. He can do quite a bit.
That's very interesting. Well, that's fine on here on the Earth, but is it the same if he was up on the moon?
It wouldn't be on the same on the moon. No, on Earth, where this test was just run, we're at 1G. But it really, in order to determine how much effort is associated with working on the lunar surface, we must somehow simulate the lunar gravity. The lunar gravity being approximately 1/6 that of the the Earth. Now, we have 3 ways of achieving this. The first is a 1/6G simulator, which we've had fabricated here. It is a series of levers counterbalanced with weights, with a man hanging on one end of it. He's like one portion of a giant mobile. And by counterbalancing and overweighting one side, we can give him the effect of 1/6G. However, there's a great deal of mass and inertia associated with this rig. It weighs several tons, And in order to overcome this, we use several ropes and men on the end of them so that it won't take over from the man. Then there's a second one, and this is the Langley simulator, where a large pendulum, a very long pendulum, is attached to the man sideways, who attempts to walk as though he were walking along the side of a building. He's held by 6 or 8 tethers from various points of articulation on his body. In this manner, we can vary the point or pivot of the pendulum so as to simulate, again, 1/6G on his boot soles. But probably the best way of doing it is in the KC-135 aircraft, which through flying parabolic arcs can simulate between 35 and 40 seconds in duration 1/6G. And we've done most of our tests. Our most effective tests are done at altitude in the KC-135 craft. Now, these are supplied to us by the Air Force.
Well, when you put all this together, what does a spacesuit nowadays cost?
Specifically, the Mercury spacesuit ran between $6,000 and $7,000. The Gemini spacecraft spacesuit will run ultimately approximately $35,000, and the Apollo suit, when it is complete on a unit basis, will run somewhere around $150,000, including the portable life support system.
I see. Well, do you feel that this Apollo suit is the ultimate in spacesuits?
No. There is another suit system that's being developed, undergoing the same series of tests that have been imposed on the other suits. And this is a hard suit. This suit is fabricated of aluminum and honeycomb.
So like a suit of armor, then?
It's indeed a suit of armor, with the exception of the visor, which is a plastic. The joints are covered with cloth just for purposes of protection, keeping dust and so forth out of them. But many of us feel that a suit of this type is the ultimate in lunar exploration.
The extravehicular mobility unit for Project Apollo is, as we've seen, not the final word in spacesuits. Research is already underway on even more advanced systems. But no matter what these systems may look like, they will certainly benefit from the experience gained with Apollo's EMU. Today, we visited the Manned Spacecraft Center in Houston, Texas. I'm John Fitch, MIT science reporter.